All right, everybody. So this is the water chemistry lecture. This is unfortunately one of the hardest lectures, I think, to conceptualize. So pay attention. We'll probably also hit up a lot of these topics later on. So, when we have water, when you have a cup of water, it's not just H2O in there. There's other stuff in there. Uh, especially as you get water that's much more turbid, there's certainly more going on here than just H2O in there. So we can think of what is in water as the solids, okay? And there's total solids, and that total solids is made up of two things: total suspended solids and total dissolved solids. Now, suspended solids are essentially just the stuff that is kind of like only in the water, pretty much because it's the water is moving a little bit. So you take a 2-micron filter and you filter it out, and it's pretty much just sediment and phytoplankton. Okay. Now, there's smaller stuff there that is the dissolved stuff. These are things small that will pass through that 2-micron filter, and like salts and ions are truly dissolved. Like colloids and really, really, really tiny particles aren't truly dissolved, but we have to cut a line somewhere, so we just use that 2-micron filter. Okay, so you can, basically, to figure out how much total solids there are, you put water through a filter. You take that filter off and you weigh how much crap is on that filter. And then you basically boil away your water and find out how much stuff is left in your little beaker that you were boiling it in. Obviously, you'd have to weigh it first and weigh it after, but you know what I'm saying. And that's how you figure out those total solids. Now, we're going to spend most of the time thinking about the dissolved portion of that, right? Because that's really what we're talking about. So Le Chatelier's principle, if you go back to your introductory chemistry course, says that in really any reaction, it's a two-way reaction, where you have, we usually think of it as products going to reactants, but there's an equilibrium point such that if you have enough reactants, you can go back to products. And so the chemical transformations that we'll be talking about today, the reactions we'll be talking about, are all, their equilibrium point is such that if you add product, you get more reactant. If you add reactant, you get more product. That's what basically Le Chatelier's principle. So I would check out this YouTube video. The link will be in the description, because it really does a really good job of explaining that Le Chatelier's principle. So we'll be talking about the carbon cycle as the main portion of this lecture. And carbon, what we're really going to be talking about is carbon dioxide, right? How does carbon dioxide get into the water? Well, it either diffuses or there's organisms inside in the water that are respiring. Precipitation can bring, water moving into it, or either via precipitation or runoff can bring carbon dioxide into the water. Now, carbon dioxide is extremely soluble, meaning there can be, at saturation, there can be 200 times more CO2 than there is oxygen. So water has like a lot of CO2 in it, and that's it's not necessarily a problem like it would be in air, right? If we have too much CO2 in air as we're breathing, we can't do that. We can't deal with that, right? But the organisms that live in water don't really care how much CO2 it is. They're really only concerned about the oxygen in it. Now, there's a reversible reaction where when you get CO2 in water, some of it combines with that water and makes carbonic acid. Now, what happens though, it's only 1/400th of the CO2. So if you put in 400 CO2 molecules, you'll on average only really make one carbonic acid. That's not really true the way you should. That's not like what's actually happening, right? So what's happening is there's plenty of CO2s that are combining with water and going to carbonic acid. But then there's also plenty of carbonic acids that are going back and turning into CO2 and water again. So what's actually happening is that the equilibrium point is such that 1 out of 400 of those CO2s turn into that carbonic acid. Okay. So carbonic acid in itself is, in the name, a weak acid, right? So what happens is some of these hydrogen ions, because that's what an acid is, remember, dissociates to create a hydrogen ion and a bicarbonate molecule. So real quick, what I would say is we're going to be talking about carbonic acid, bicarbonate, and carbonate. Memorize those. Remember what they are, because I'll be using those terms a lot. Hopefully I won't say them incorrectly, but definitely memorize those terms. Okay. So bicarbonate itself then can dissociate to produce what's called carbonate. Okay. So bicarbonate is even a weaker acid. Now, when I say that, let's go back here, that 1 out of 400 of the CO2s make carbonic acid, it's then fewer that make bicarbonate and fewer in itself that make carbonate. So it's like every step in that reaction is basically more rare in happening. So because of Le Chatelier's principle, if you were to change the pH, what you do is you can change the concentration of carbonic acid, bicarbonate, and carbonate. So if we see, it all has to do with pH, right? Because pH, what that is the concentration of hydrogen ions. So remember, to the left here is lots of H plus, right? So lots of hydrogen at low pH. And this is, few H plus. Okay? So we'll talk about how adding, acids to a system can change what's going on here, and we'll need to be thinking about this equation in several different contexts. But I guess we'll just wait there. But what you're supposed to take away from this graph is that at low pH we see a lot of carbonic acid. At middle pH we see a lot of bicarbonate, and at high pH we see a lot of carbonate. So what we actually have then is this equation here, this whole big equation. So going from carbon dioxide with water to make carbonic acid, then that hydrogen ion dissociates to make bicarbonate, hydrogen ion dissociates to make carbonate. So let's say we have a system that has, let's say we're at a high pH water. Okay, let's say the pH is at 12, which is pretty much like pure ammonia, but let's not consider that. Let's just say the pH is really high for some reason. Okay. Now, as you add hydrogens, what you're going to be doing is adding products. So it's going to be like adding the products being this hydrogen ion. So as you add that as you add that hydrogen ion, you're bringing the pH down, and essentially, because you're adding products, the equation then also goes to the left, and we get to go back to the left on the equation. Okay, and that's why we see these different species of carbon, the carbonic acid, bicarbonate, and the carbonate, being pH dependent. So if you were to add, so let's go through that one more time. You add hydrogen ions, it lowers the pH, and it makes the equation go to the left, and then most of them, we're at a situation where most of the carbon species are at this carbonic acid. Alternatively, if you were to start over on the left and make the pH go up, everything goes to the right then. Okay. The thing is, it's really not that it's more complicated than that. So what actually happens when all these things disassociate is that you get these two offshoots, because when you have here bicarbonate itself then can combine with water to create a hydroxyl group and then your carbonic acid. Okay, so same thing happens then over here with carbonate, except you're making bicarbonate there. So what happens? What happens when you add an H plus to this equation? To this system, I should say, not necessarily this equation, but to this system. Now, the easiest thing for an H plus, it doesn't matter where we are on this this situation, this pH scale. Wherever you add a hydrogen ion, what it's going to combine with is this OH minus, right? It creates water. And essentially what happens is the pH doesn't change. Now, why is that? So if you add a single hydrogen ion and it combines with this OH, essentially taking this out of this equation, and what happens is this equation then just kind of like chunks over one spot to the right, and then you get another OH coming out. So this is why we call it the carbonate buffering system, because this addition of a hydrogen ion essentially doesn't actually change pH until you run out of carbon in the whole system. So I forgot where we were going. Let me talk about this, and we'll come back to the buffering system here in a minute. But at this low pH system, what we're having is a dominance of the carbonic acid, even though there is some bicarbonate available. At that high pH, we have a lot of carbonate available with a little bit of bicarbonate, and mid pH, you're dominated by the bicarbonate. So, okay, I'm sorry. Let's go back to this. What happens when you add a hydrogen ion? Remember, so when this hydrogen ion will combine right here, and what you'll get out of it is a water. And since you just think about maybe just this equation, since you're adding this product, well, I should have gone like this, right? Since you're adding this product, then the equation will go down one here, and these will kind of all filter out to the right. Oh my gosh, I'm sorry. All filter out to the right and come down, and the OH will be replaced. Now, alternatively, what happens if you were to add an OH to the system? And I'll just do it over here. You add an OH to this system, you have more, in this sense, products, so the equation goes up and then over chunks kind of over one to the left. And pH doesn't change. Now, essentially what's going to happen then is pH won't change until you run out of carbon in this system, and then the pH will fall rapidly. And this is actually what's happening in your blood. So what we see is that you can artificially change how, well, I shouldn't say artificially, you can change what species of carbon is available based on the bedrock. what is like essentially dissolved in the water. So if you look at limestone, what it is calcium carbonate, and these are all like tiny little corals and tiny little organisms in here that had calcium carbonate shells. And so when you um, take this calcium carbonate and put it in water, what it does is it stabilizes, puts a lot of carbon and stabilizes pH at this like 8.2 number. Okay. So in places that have a lot of limestone bedrock, like a good portion of the Midwest, we have really stable pH. Whereas if you look at the top of mountains in the Colorado Rockies or in the Northeast where it's all granite, um, they don't have a lot of limestone, and their water then is not as stable in pH because it doesn't have as much of this carbon dissolved into it. So let's look at this now a third way, is essentially what happens if you increase CO2? What happens to the system? So if you're adding a bunch of CO2, you'll have, if you add 400 extra CO2s, you'll create one more carbonic acid. And, one of a small portion of those carbonic acids will turn into bicarbonate and carbonate, right? So as you add CO2, what you're going to be doing is making the equation continually go to the right. And what happens then to the pH is due to this, you're adding hydrogen ions and the pH goes down. So if you add CO2, the equation continuously goes to the right and you're adding hydrogen ions, And you might ask, well, don't these things offset, right? These OHs, don't they offset? And the answer is no, they do not, because remember, every time you go to the right, remember, this is 1 in 400. This is 1 in, I don't know, let's say 2,000. I don't know that actual number. And then this say 1 in 10,000. Okay, so the OHs, as you're adding CO2, you'll also add OHs here, but at a smaller number or a smaller rate than you would be adding these H's right here. So these H's kind of overpower these OHs and you get a net pH decrease. So this is what's happening, on a global scale, and this is why we have acidifying oceans, because as we increase CO2, we're getting more of this hydrogen right there. And this one, but same process, right? So what about the carbon cycle? Like, there's a lot more to it, right? There's carbon going through all sorts of different pathways in a lake. We don't need to know it this closely. What I would really, the way I could like you to think about it is, how does carbon dioxide enter the lake? How does it get transformed in the lake? And then what happens to the pH essentially because of that? So what we see is carbon dioxide is essentially at equilibrium with the atmosphere, right? CO2 is not changing fast enough that the CO2 can't like get into the lake, right? It's changing fast, yeah, but that kind of chemistry is faster. So, but what we see is that photosynthesis really reduces free CO2 in the water column. That's what photosynthesis is doing, right? As plants are growing, they're taking up carbon dioxide, and essentially getting rid of it. So what we see is on a daily cycle, if you were to put like dawn here, dusk, and then the next dawn right here. Oops, running out of space. Sorry. What you would see is, if we look then at pH, pH would, start at some number. Doesn't matter really what it starts at, but pH would start to go up throughout the day, and then once you reach dusk, it would start to decrease, and then you'd have this repeated cycle where pH is decreasing at night and increasing during the day. And that's because CO2 during the day is being taken up, so pH will go up. And at night, no photosynthesis is happening, CO2 is just being released, and the pH will go down. And it'll depend on how buffered the system, how much carbon is actually dissolved in that water, to see how much it'll go up and down. All right, so that's it for carbon. I want to talk a little bit about nitrogen. Now, nitrogen is an interesting element because it is normally in how we find it 70-some% of the atmosphere, right? Was it like 78% of the atmosphere? Somewhat a little less than that. But what we have is triple bonded, N2 has this triple covalent bond. Now, that triple covalent bond is extremely strong. There's really only two ways that you can naturally to break that bond. One is with lightning, and the other is with nitrogen fixation. Now, nitrogen fixation is done by bacteria. So this is a cyanobacteria that has this special cell called a heterocyst. That looks very different than the other cells. Here's a baby heterocyst that's going to be growing here soon. And inside that cell, there's no O2, no oxygen, right? Because what you're doing is you're taking N2 and turning it into ammonia, NH3. And if you ever have oxygen in there, what it will turn into is like NO3, not what plants want to use. But diatomic nitrogen here, N2, this triple bonded nitrogen, is completely useless, right? We breathe it in and we breathe it out. We breathe it in and it dissolves into our blood. Our body does nothing with it. It comes out of our blood, goes back into the air. So nothing really happens with nitrogen, okay? For it to be biologically active, it needs to go through this fixation cycle. Once it gets fixated, and then it can be used by any plant, essentially, whether we're talking about algae, vascular plant, moss, whatever, it can be used. It'll be taken up. This nitrogen or this ammonia is, you'll see those out on farms, those anhydrous ammonia tanks. It's essentially just this NH3 that they put into the ground to use as fertilizer. Now, nitrogen can further be processed from ammonia, and this is done either by bacteria. Some plants will do it, but they'll put oxygens onto it to make it into nitrate and then further into nitrite. This requires an aerobic environment. Aerobic meaning oxygen. Not surprising, if you're going to put oxygen onto ammonia, you need the oxygen to begin with. So the nitrate and the nitrite can also be used by plants. Remember, ammonia can be used too. Plants prefer to take up ammonia because they have to do less to it, essentially. It's kind of like, they don't have to process it before they can actually use it within their tissues. So, excuse me. Once you then have nitrate and nitrate out into the system, if you ever run like fish tanks, having too much ammonia, too much nitrate in your tank is really dangerous for your fish. You need to have something to get rid of it. And this is why if you have a fish tank, you should be changing your water. Some people do it completely biologically with having plants and mostly bacteria. And what they'll have is denitrifying bacteria. And this is the reduction of nitrogen from some NOx here. This X is referring to either a 3 or a 2. and it turns it then back into diatomic nitrogen. This again requires an anaerobic environment, so we see this happening in the sediments. Anytime you have shaded sediments where you're not having a big influx of water with oxygen going into it, denitrification can happen, and it's really, really important for to not pollute certain systems. One of the reasons why we think we have the Gulf dead zone is because we've gotten rid of all of the wetlands along the Mississippi River system, and there is not enough denitrification going on. And so we get a lot of extra nitrogen in the water in the Gulf of Mexico, which causes that great huge dead zone. So let's move on to phosphorus now. Phosphorus is extremely important in aquatic systems because it is basically the main thing that limits the main limiting resource, right? It limits biological productivity. If you add a pound of nitrogen to a lake, you'll see an increase in growth. If you add a pound of silica for diatoms, you'll see an increase in growth. But if you add a pound of phosphate, you'll see a huge increase in growth. Okay, this is the phosphate. What we're looking at is when we're thinking about phosphorus, I just use the term phosphate. Usually I'm talking about orthophosphate. It's one phosphorus with 4 oxygens around it. The thing is, phosphate is actually really hard to measure. It is used so quickly that it is super hard to actually like measure because it's just sucked up so quickly. There's some really interesting studies where they look at you know annual mean phosphorus, and there's this really close correlation, well, for ecology, a relatively close correlation here, where you get increase in productivity. This productivity is measured by how much chlorophyll is actually in the water. So they've done this like really cool study where they did there was like an figure 8 lake, and they put a big plastic barrier across it, added phosphorus to one side, and this is what they got: a bunch of a eutrophic condition with a bunch of gross algae and a very clear condition. I'm not sure if this experiment is still going, but obviously adding a little bit of phosphorus has a huge impact here. The last thing I want to talk about then is silicon. Silicon is essentially glass, right? And it's most important to diatoms. Some plants like this horse-tailed equisetum will use it to strengthen their cell walls and for structure. Sponges use it in their bodies to make these little Mercedes symbols, but they're spicules, these little sharp things. But diatoms are doing the most important thing. And what we can see is that silica is really tied to diatom abundances. Okay, so if you look at a seasonal succession of phytoplankton, what you see is real early diatoms increase very greatly. And you can see that this is October, December, February. This is essentially winter, and what you see is a pretty early bloom of these diatoms. But as those diatoms bloom, that's right here, silica crashes like crazy, right? Essentially there's no more silica in the water, and such that the diatoms then crash. All right, so we don't have any more diatoms in the water, and green algae then takes over. And all this time, throughout the summer, silica is relatively unreacted. Like if you throw a glass bottle into the water, it doesn't dissolve, right? It does sort of, but it takes for flipping ever, right? The thing is with this is the diatom shells that we're talking about here. They're so small that they do actually get dissolved back into the water, and silica starts to go back up. And when you see it go back up, after the water starts cooling down in October, you can oftentimes see a diatom bloom again because silica is at high enough level, and we see a smaller bloom that's a little bit more temperature attenuated because of temperature, but then essentially the water gets too cold and the diatoms die off, and then we come back into January, February, March, and you get another bloom. But in this time between November into March, the silica has a time to increase back up to the high levels that it was at. All right, that's it for all the different major chemical cycles. With that, I'll see you later.